So, take it away.
Okay. Thank you. Can everyone hear me all right?
Yes.
Excellent. Well, good afternoon. Thank you for joining us for this afternoon's talk. We're going to tell you a little bit about our research, which is on paleontology, on primates, and touches to some extent on the geology of Oregon. Thank you to the Yachats Academy of Arts and Sciences for inviting us to be here, and thank you for being here. So my name is Jonathan Perry. I'm originally from Alberta, Canada, where I grew up with a passion for dinosaurs. Like many kids. Unlike many kids, I never grew out of that passion for dinosaurs. So this is what I do for my job. I went to the University of Alberta and did a degree in paleontology, and during my summers between terms I worked at the Royal Tyrrell Museum of Paleontology, which happens to be the world's largest museum dedicated purely to fossils. Great place to work. After that, I did a master's degree in primate paleontology, specializing on the relationship between tooth shapes and food properties, and how teeth affect foods and how foods affect teeth over evolutionary time. And I built a chewing machine that's shown here to simulate chewing, and tested out a number of different primate dentitions on a number of different foods to compare their efficiency and food breakdown. And incidentally, teeth are a really important thing to know about if you're working in mammalian paleontology, because 99% of the fossil record of mammals, including primates, is just teeth. They're very hard, they preserve very well. So if you know something about teeth, you can maybe say something about diet in the fossil record. And so after I did that, I moved to the United States, where I did my PhD at Duke University, specializing on how lemurs chew. And that's when I started to do paleontology fieldwork in South America at sites that my advisor was working on. And we'll talk a bit more about those sites in a little bit. Since then, since my PhD, I've traveled around a number of places in the US and done fieldwork in lots of parts of the world, including in Saskatchewan in Canada, closer to where I'm from. And we moved to Oregon in 2021, and in 2022 we started a field project out in the John Day National Monument in eastern Oregon. So that's who I am, and I will now turn it over to my partner Anelia, who will talk about who she is.
Thank you very much. Yeah, so I'm Dr. Anelia Hogan, and we've been collaborating for a while now. But we've got pretty different backgrounds. So I started with primates. So I kind of began my academic career up at the University of Washington in Seattle, where I grew up. And I did primatology there, worked with monkeys for a really long time. And from there, I continued working with primates and became a lab manager at the University of Chicago. But I didn't live in Chicago, I lived in Puerto Rico. So there's a little island down there where in the 1930s they brought tons of monkeys over from India and just let them range free on this island. And it's now a laboratory for studying their behaviors, etc. So I spent quite a long time down there, just 8 hours a day watching monkeys all day. It's really fun. But I'm one of these people who didn't get into paleontology as a kid. I had what you might call a coming to Darwin moment in my mid-20s. So there's one day I was with my family, we were out in Glacier National Park. So we decided to go up the Grinnell Glacier Walk, and at the top, we get to 7,000 feet above sea level. And I looked down at my feet and I noticed there were these strange kind of circular formations. And I suddenly realized that these were bacterial mats from 1.5 billion years ago. And these were the mats that were cyanobacteria that actually produce most of the oxygen that we're breathing right now. So these are these bacterial mats that basically made our lives possible. And this was just the moment for me where I realized the power of fossils to really tell us everything about our history and how we fit into the world. So I went back to U Chicago, and I decided to join the fossil lab there. So I started by just volunteering, worked my way up, started working there. And I eventually got enough experience that I applied to PhD programs. And I went to Johns Hopkins Medical School, and I got my degree in anatomy and evolution. And most of my research there is all on the development and evolution of the olfactory system in birds and dinosaurs. So if anybody is interested in talking about that at the talk, I love talking about that stuff. Also really interesting. And so over the years, I've also done tons of field work. Went into Wyoming, you can see here digging up a stegosaurus. Been out to Colorado, looking for other really small mammals, similar to the primates that we're talking about today. And then the two of us went to Argentina, continuing to do more primate work. And now continuing this work in Oregon together on more primates. So kind of like me before my epiphany, a lot of people, when they hear the word paleontology, they automatically think fossils. And they automatically think dinosaur fossils. But I just want to take a moment and kind of introduce paleontology to you as a field that's so much more than just that. So, when we're looking at all of these fields, what we're thinking about here is not just answering questions like, did dinosaurs have feathers? They did. But what we want to know are what are the mechanisms that really dictate all the possible different avenues down which life on this earth can and has adapted over a really long time. So we get things from unicellular organisms to the complexities of things like clonal forests and even the human brain. And looking at these things, we're not just looking at what is possible to evolve, we're also trying to consider what is impossible, what can't evolve. So in this way, we're also looking at what are the boundaries of life itself. So these are really huge questions. So they're looking at really big, emergent biological processes. And in this way, we're just trying to figure out, where do we fit in all of this and how is all of life connected? But to do this, it really takes the integration of tons of scientific fields. It's not just paleontology. We're using embryology to understand how do you even build an organism from one cell to what we see here today in our own bodies. We're using genetics to understand how to code for building all of those, but also to understand how everything is interrelated over due time. But there's so much about these two subjects that we also can't answer yet. We don't know exactly what genetics code for and what they look like once they're coded. So for this, fossils are really necessary. We really need these fossil records to see what are the possibilities, what can things evolve into. And so fossils are what we're going to talk about today. But we're going to concentrate on a part of the tree way after dinosaurs, but way before us. We're going to talk about really early primate evolution. So we know that today there's lots of different primates, tons of diversity of primates all over the world, but kind of focused around the equator. And we know from their fossil record that they used to live all over the place. So how did they get there? What we're going to talk about today is how these little monkeys and primates made their way, globetrotted across the continents, and even made their way here to Oregon. So first, we're going to answer a couple of major questions we always get as paleontologists. How do you become a fossil? So the first thing that happens, obviously, is you have to die. And the next thing is your body decays or is eaten away until most of what's left is really just bones. Sometimes you have some other parts left, but usually not. And then slowly, over time, we get layers of sediment that come and kind of cover and protect these bones. And they build up and they build up. And this takes a really long time. So we're talking hundreds of millions of mud, sand, and sometimes volcanic ash, burying this structure and this organism really deep in the underground. But for us to get to it, it needs to be uplifted. So this happens with lots of geological processes. But first, it has to turn to stone. So we have this mineralized water that comes in and actually slowly replaces the bone, turning it into the stone itself. Then we have this uplifting process, and we see it lifted up higher to the surface of the earth. And then through erosion, in addition, through wind and rain, for millions of years, it gets exposed to the surface. And this is when, at some point, when we go out, taking a look, trying to find these things for weeks and years and months, eventually, we come along, and we get super excited. So that's kind of a description of the basic way that you can become a fossil, but there's also lots of other situations that create different types of fossils. So I wanted to talk just about a few of those, just because it's extremely interesting and tells you different things and different information from the past. So the most common, and the one I kind of just described, is this process of permineralization and replacement. These are slightly different, but usually work in tandem. So permineralization involves the incoming of these mineral ions and filling in spaces in the bone. Replacement is actually replacing the bone itself. So here you can see an example of these two things working together. All these little bubble-like structures are little holes in the bone that create something called trabeculae. And so those inner parts are being filled in through permineralization. And then this bone matrix, this white part surrounding each bubble, is an example of replacement where the bone itself is being replaced. And together, this process creates almost a perfect replica of the bone that was there. So this is an example of how we get these amazing dinosaur fossils that you can see across the world, and it preserves it in 3 dimensions. We can also get them in such a way that these kind of recent Homo ancestors of ours replicate their skulls in a way that looks like they could have died yesterday. So amazing preservation from these 3-dimensional fossils. Another type, something called trace fossils, kind of explains itself. They give us different kinds of information. So the most common one that we talk about here are things like footprints. But we can also get something like footprints for smaller animals. So this trace fossil, or ichnofossilization, can preserve really fine details, where we can see this little trilobite and how it walked across the seafloor. So this is giving us all kinds of information about locomotory patterns. And one other one that's quite common is molding and casting. So you can see an example of here, these two juxtaposed. So this is when there's an organism that then degrades, but leaves behind evidence it was there. So this is a mold of a shell just like this. You can see the difference between where the actual shell itself was preserved and neighboring structures disappeared, leaving just a mold. Very common elements like this we see in ammonites. These are little shelled cephalopod-like creatures, kind of like octopuses and squids. So when you see these, which you probably can in lots of fossil shops, most of the time you're not looking at a shell. You're looking at the inside structure that has been cast from the shell. This is one of the preservation styles that I've worked with almost most. A lot of my work has worked on brain endocasts. So this is when the internal structure of a skull gets preserved, and especially in birds and humans, because the brain is so directly close to the skull, you get a perfect cast of what their brain looks like. You can actually look at the evolution of brains over time. So that's a perfect example of the different kinds of information you can get. And one of our favorite types, just because they're so incredible, come out of things called Lagerstätten. And this just means storage place. And the reason it's called that is because it preserves animals and even soft tissues so well. So these kinds of fossils you're going to find in kind of anostic environments, so we're talking swamps, bogs, places where oxygen cannot get to them to degrade them before they're just skeletons. So what we get is actual soft tissue preservation. The downside to this is that because they're under so much pressure from the sedimentation, they're often flattened. So we don't get all this 3D structure. Not great, but what you do get is even better. So in examples like these fish, these Nidia, these are all from Green River Formation, really common across Wyoming, Montana, and you can probably see them in all the rock shops around here. But you get things like scales and fins preserving. And probably the most famous one is this one of Archaeopteryx. And you can see how it actually preserved the entire wing structure, not just here, but all the way down on the tail. So this is one of the specimens that actually completely revolutionized our ideas about the dinosaur-bird transition and how that occurred. And one of our favorites is this little guy here. This is Darwinius, also known lovingly as Ida. And she was found in Messel, Germany. She's about 47 million years old. And this is a little fossil primate. It's probably the best preserved fossil primate in the world. And it's hypothesized that she lived above a swamp and one day was overcome by some swamp gases and fell into the swamp. But she's so well preserved that we can see details like a broken wrist that might have contributed to her demise and falling in. We can also see some of her fur preserved all around the body. And the most interesting and amazing part is that we know exactly what her last meal was. So you can see the stomach contents actually preserved in this fossil. So these Lagerstätten fossils are just an endless amount of information for us. They're some of the best fossils we can find. This is the most common question we get. How do you find a fossil? Where do you even begin? And honestly, it's not as complicated as you might think. So it does require a little bit of geology, but thankfully geologists have gone out and they've created these amazing maps. So you can see here, everything is color-coded on the right, and it tells you exactly what age the surface area and parts of these are. So that's kind of the beginning, is knowing what kind of age of rock you want to look at. So knowing what fossils you're looking for and how old those fossils are, you can then look at these maps and know exactly where to start. So you can see here, these are all Eocene colors. If we want to go out and find an Eocene primate, there's a lot of possibilities here. This is all Eocene, this is all Eocene, this is all Eocene. That's a lot of space. So you need to kind of narrow it down a little bit more. So the next step that we use is looking at satellite imagery, or just regular maps. Because what we're looking for, if we go out here, we're going to go for a walk in the forest. We're not going to find fossils on the forest floor. There's too much debris built up. What we want are arid and desert-like situations where there's low brush and lots of erosion. So we want high turnover where these things are eroded down. So once you know where you want to go, so we know over here, there's lots of desert out here in Eastern Oregon. So this is a really promising area to go look at. Next thing you do is you just go and look for it. That's it. You just go prospect. So on all of the digs I've been on, we've spent several days, not just digging, but walking around and looking for new fossils coming out. And the great thing is that it's not just paleontologists that can find fossils. Anyone can do it. And some of the most amazing fossils have actually been found by just members of the public walking around. Inspirational, right? So the great thing about Oregon is that there's tons of fossils here. So this is a map by Ray Troll, who's one of our favorite paleo artists. And you can see just how much diversity of fossil life there is across the entire state. And it's everywhere. We're getting everything from dinosaurs and pterosaurs to mammoths. We even have some of the best preserved seeds and plants coming out of Oregon. These are some of the best preserved ones in the world. This is a really premier site for fossils that I think a lot of people don't know about. Oregon is kind of a hidden gem for fossil productions. And we even have this little guy, who we're going to go into talking about next. And this is a little fossil primate that was found right here. Our own little Oregonian primate. So as a paleontologist, I have to be responsible. So when you're looking for fossils, you are responsible for knowing exactly what the laws are. So you have to know where you are, what kind of land you are on, and what the legality is of collecting fossils there. So it's always illegal to collect on federal and state land or parks. But in the Forest Service, you're allowed to collect a reasonable amount of common invertebrate or plant fossils. So no vertebrates. If it has an endoskeleton or any bones that look like ours, it's a no-go. But common invertebrates, you're responsible for knowing if they're common. And plant fossils are totally fine. Bringing us kind of close to here, any of the loose fossils that you find on public beaches around here are totally fine to take. Just don't go digging into any of the cliffs, etc. And you also can't sell them without a commercial permit. So just keep that in mind. So really, the safest place to go is on the private land, with the permission of the landowner, of course. But also as a paleontologist, I have to encourage you that if you ever do find something that you think is rare or really interesting, take it to an institution, bring it to a museum so that we can study it, so that everyone can enjoy it. And in the words of a famous archaeologist, People have long reason to be zoos. Okay, so that's my spiel about being responsible. Next, we're going to have Jonathan start us off talking about the primates.
Okay. Thank you. So, at this point, most of our paleontology focus is primates. We find lots of things, but that's really what we're hoping to find wherever we go. And so I want to take a minute to talk about what is a primate, because primates are familiar to most people, but also confusing sometimes as to what belongs in the group. So we'll talk a little bit about the features of them. Primates are mammals. They're an order of mammals, and they seem to appear in the fossil record roughly the same point in time that the dinosaurs go extinct. A little bit before we get the best fossils, right after the extinction of the dinosaurs at the beginning of the age of mammals. Nowadays, so they probably evolved from something that was small, nocturnal, maybe shrew-like, and a placental mammal, and now there are several hundred species of primates today, all of which are vulnerable to extinction and endangered to some degree. And there are some interesting reasons as to why that is. Primates are especially vulnerable to climate change because they have a lot of requirements. They're very needy mammals. They require warm conditions for the most part, humid conditions, access to fresh water, and access to ripe fruits for a good period of the year. So those are some of the vulnerabilities that we, as primates, because we are primates, share with our primate cousins. So primates can tell us a lot about ourselves, our evolutionary history, and what we are vulnerable to. And so as a group, primates can be characterized in general as having large brains, having very dexterous hands and feet, having good eyes, often with color vision, complex social systems, and extended periods of parental care. And some of these things contribute to our vulnerabilities because we require a lot of parental care for our offspring and we have a slow reproductive cycle. Another thing about primates is they tend to depend on trees to at least a large extent to make a living. Some of them get out of that, but most of them are dedicated arborealists. Here are some of the groups. These are all of the groups of primates, actually. Some of them are going to be more familiar than others. And so if we start at the bottom, we have apes, including us very strange humans and our closest relatives. We have monkeys, which come in two kinds. There are Old World monkeys in Africa and Asia, and there are New World monkeys in South America and Central America. And actually, the Old World monkeys are more closely related to apes than they are to the New World monkeys. But the two types of monkeys share some superficial similarities. And then at the top, we see three types of primates that are maybe the most primitive of primates. And they are the lemurs, the lorises, and the tarsiers. And I'll talk a little bit about those. So if you focus in on the prosimians, they're all really cute. That's what really groups them together, is they're cute. So on the left, we have the lemurs, all of which, believe it or not, are native to Madagascar, large island off the coast of Africa. All lemurs are from there. Their cousins in the middle, the lorises and galagos, are native to continental Africa and to Southeast Asia, places like India and Borneo. And lastly, the tarsiers are some extremely weird primates that are actually more closely related to monkeys and apes, but they still have a lot of primitive features, so we can talk about them with the lemurs and lorises as prosimians. And I just want to focus for a moment on how weird tarsiers are. They're tiny, they're sort of palm of the hand size, and they look like little gremlins. And notably, they have enormous eyes. So their eyes are so big they can't move them around in their eye sockets. And each eye is as big as the animal's stomach. So you could say literally their eyes are bigger than their stomachs. And each eye is bigger than the brain. They're also completely carnivorous. So the only animal matter they ingest is in the stomachs of their prey. Nowadays, they're rare, and they're restricted to islands in Southeast Asia, like the Philippines. But in deep time, 50 to 30 million years ago, the ancestors of tarsiers actually made up one of the most important fossil groups. They were very diverse, and they ranged very widely across the world, including in North America. Here are some examples of old world monkeys, just to show you the breadth, the diversity of them. And they include such familiar things as baboons and mandrills, geladas, guenons, vervets, macaques. And here are some new world monkeys, things like marmosets and tamarins, capuchins, squirrel monkeys, howler monkeys, spider monkeys. And they have some major differences between the new world monkeys and the old world monkeys, but one of the most interesting ones is that all new world monkeys are arboreal. So they spend their whole lives in the trees, some animals never coming down to the ground. Whereas many of the old world monkeys have adapted to life on the ground and even living in rocky cliffs for some of them. Here are the apes. So our closest relatives, and they're shown here with a diagram that represents their genetic relationships. So on the far left, we have the lesser apes, the gibbons, and then orangutans, gorillas, and then the two species of chimpanzees are our closest relatives. Here's a map of the world showing where primates live today. And the areas where they live are represented by pictures of those primates. So you can see that these areas are primarily in the tropics. They're near to the equator. And so here are some New World monkeys in South America and Central America, Old World monkeys in tropical Africa and tropical Asia, apes in roughly the same locations, lemurs in Madagascar, lorises in continental Africa and Southeast Asia, and tarsiers mainly in these Southeast Asian islands. So that's where primates live today. They're pretty much stuck in the tropics, except for humans. Compare that with this map, which shows not only where the living primates are in black, with fossil primates from two different slices in time where the Earth was really warm and wet. So you can see in these hatched areas, primates live far beyond the modern range of where we live today. And that was enabled by the difference in climate and the associated differences in vegetation. So here I'm going to march you a little bit through the epochs of time since the demise of the dinosaurs. So this is now the age of mammals, the first epoch of which is the Paleocene, 65 to about 56 million years ago. And the symbols on the world map, little triangles, are fossil primate sites. So this is where actual primate fossils have been found. And I want you to notice that a lot of these are way, way north of where primates are found today. So the Paleocene was much warmer and much wetter than it is today. Forests were all over the world practically. The next epoch, the Eocene, was really the heyday of primates. The Eocene experienced the highest temperatures and the highest rainfall that we've had since the dinosaurs went extinct. And so there are a number of primate fossil sites in lots of parts of the world, including this one way up here in Ellesmere Island in Arctic Canada. Monkeys living in the Arctic. And as it turns out, there was probably a very nice forest corridor all through the Arctic that enabled primates to disperse from Asia to Europe to North America and back very, very rapidly, in some cases with a single species being present in all 3 continents. So that was really the ideal time for primates. That was soon to end in the next epoch, the Oligocene. So at the beginning of the Oligocene, things went bad. The Earth got a lot cooler in general, much more arid, and much more seasonal. And so we saw a retreat of rainforests and extinctions of major groups of primates. So now you're starting to see it's getting closer to the modern pattern of primates with a few stragglers, one of which, by the way, is in Oregon. You'll notice that primates first get to South America in this epoch. The next epoch, the Miocene, is getting closer to today, only 5 million years ago at the end. Even cooler, even drier, with the spread of grasslands and a lot of animals that exploit grasses. Some primates manage to make it farther north because they have special adaptations for living in cold, dry climates. But for the most part, it's looking like the map of primates today. So, one of the most outstanding, weirdest, most mysterious questions in the history of primate evolution is, how did primates get to South America? They seem to have gotten there towards the end of the Eocene, beginning of the Oligocene, about 26 million years ago. But at the time, South America was an island, greatly separated from any of the other parts of the world where primates lived. So how did they get there? The first primates that show up in South America have a lot of anatomical resemblances to the African primates at the time. Very different looking from the North American ones at the time. So probably Africa is the source. And believe it or not, the prevailing theory is that terrible storms were constantly hitting coastal West Africa. In some cases, pulling vegetation off of the continent, sending it out into the ocean like rafts. And some of those pieces of vegetation probably had little primates in those trees. And so the primates rafted across the Atlantic Ocean, made a landfall at some point in what's now Brazil, discovered forests, and colonized them. This is actually our most likely story. So I'm going to kind of focus a little bit now on South American fossil primates. So during my graduate work, I started working at some fossil sites way down here in extreme southern South America. The first primates appear in South America more to the north, and then very rapidly they seem to colonize further and further south. And this implies that there were forests much farther south than there are today. And so this is actually one of the richest fossil sites in the world. It's an amazing place where the fossils appear in the intertidal zone on the beach. So it is difficult and dirty work that must take place between high and low tides. So it's very interesting work. These sites have actually been known for over 100 years. Darwin actually visited nearby. He didn't actually collect there, but they were made famous by the famous Argentine paleontologists, the Ameghino brothers, pictured here. They worked the area in the late 1800s and early 1900s. And we've been going there since 2003, and we've found a tremendous number of fossils there. In 2019, Anelia joined me in doing field work down there, and we've extended the field work that we were doing since the early 2000s to some new sites that are younger in age. We actually got engaged there. I asked her to marry me while we were on a walk in a glacier. She said yes, so here she is. Usually you don't get claps in the middle of the talk. Well, let's move on to fossils. So these are some of the things that we found there since the early 2000s. And there are some examples here that you're welcome to come and look at, and we can talk you through at the end of the talk. Since the early 2000s, we found a number of great specimens of primates. These belong to the star of the South American monkey record, an animal called homunculus, a small monkey. These are a number of skulls, and we have some postcranial bones, even some juvenile monkeys. In 2015, we found this partial skeleton with a skull, and this is the most complete skeleton of any of the early South American monkeys. We're in the middle of describing this now. In 2019, Anelia found this tooth of homunculus, which is the southernmost primate in the world, living or dead. So now I want to tug us closer to home and talk about North America for a bit. Because, as I mentioned, the Eocene was a great time for primates, and there were plenty of primates living in North America way back then, 50 to 30 million years ago. The North American primates of the Eocene are divided into two major groups, the Adapids and the Oomymiids, pictured here. Oops, I'll say something about them. So the Adapids were somewhat lemur-like. Some of them were relatively large, so about 10 kilograms, which was large for a primate way back in the Eocene. They were active during the day, and they mainly ate leaves and fruits. By contrast, the Oomymiids are that tarsier-like group I alluded to earlier, so they're a bit like tarsiers. Small, nocturnal, probably ate mostly insects and fruit. And these groups became very diverse and abundant in the Eocene of North America, so much so that at some sites, they formed the most common type of mammal at that site, even more common than things like rodents. They were really successful in the Eocene in North America, and then at the end of the Eocene, they mostly went extinct. So here's a picture of the world in the Eocene showing vegetation. So the dark blue is tropical rainforest. The medium blue is subtropical rainforest, and wait, that's green, right? It's red, green color. So the dark green, tropical, medium green, subtropical, light green is temperate forest. In the Eocene, you can see the tropical forests covered nearly the whole world, even got into Antarctica. Now the Oligocene, quite different. At the beginning of the Oligocene, there was a sudden climatic shift. Rainforests contracted to around the equator, and most of the primates that lived outside those zones went extinct. Here's a diagram of the major groups of primates over time. Notice that these Adapids and Oomymiids, really their heyday was the Eocene. They expanded, became diverse, became abundant, and then they're nearly all gone by the beginning of the Oligocene. The living primates are all descended from some kind of Adapid or Oomymiid that was actually living in the tropics. So it was essentially protected from that climate change. So now I will turn it back to Anelia to talk about a very special primate with examples from Oregon.
So as Jonathan just said, these Oomymiids and Adapid primates were really big in the Eocene, but then all of a sudden, at the end of the Oligocene, we get out of nowhere this really weird little primate, Agamohushashala. This is almost 10 million years after all other primates in North America have disappeared, gone extinct. It's a really long period of time. Yeah, Agamohushashala, I love the name, so fun to say. It's actually one of Jonathan's email addresses. Every time he gives it to someone and they have to try to spell it, their faces go white. But it's called Agamohushashala because these specimens, which were the first to be found, were all found out in South Dakota. So it's named after their Lakota language, and they don't have a word for primate in Lakota because there were no primates. They didn't know what they were. So it actually translates more closely to little cat man. And so by looking at these teeth, primatologists and paleontologists decided that these were similar to either adapids or omomyids. You can see in reconstructions, that's exactly what they're looking like little mixes between lemurs and adapids. So things like tarsiers and lemurs together. So these specimens out from South Dakota, unfortunately, all we have are some pieces of jaw and teeth. As Jonathan mentioned at the beginning of the show, this is pretty expected for mammalian primates. It's very rare to get anything other than teeth. But in order for us to kind of know more about this animal, we're really going to need more material to understand it. Because right now, there's a huge debate, especially between teeth experts, about whether these teeth are more adapid-like or omomyid-like, or whether they're even a primate at all. So then, the big surprise is when we found some of this material here in Oregon. So these are all the Oregon specimens. There's quite a few of them. We have upper and lower cheek teeth. And the great thing is that these were found in kind of close areas, all out of the same levels. So this Turtle Cove, remember, out in the Sheep Rock unit of the John Day fossil beds. So this is a dream scenario for us paleontologists here. It's a 4-hour drive from our front door. It's like having a fossil site in the backyard. And it's really beautiful. I'll show you some pictures in a second. So some things that we can see with these teeth that are really exciting and are giving us some really great hope for the future is that there have been found 2 of the same kind of teeth. So this is indicative that there's more than one individual eroding out of this material. So there's a really high probability that we can probably find more material, which is exactly what we're trying to do here. So when we moved here, we almost immediately got in touch with the National Park Service and started a collaboration with them. And ever since, we've started a field program where we go out at least once a year looking for more material of these guys. But it's not all sunshine and roses. You can see how beautiful it is out here. Camping is great too. If you've never been out there, definitely take a vacation, go out to John Day. It's really great. But to get to these sites, all of these fossils were found way up in the hills here. And to get there, there are no roads, so we have to cross the river on this hand crank cable car. Harder than it looks. And then you have to walk, an hour or two, mostly straight uphill to get to this fossil site. But once you get there, it's this huge, beautiful cathedral-like system. And this looks exactly like what I was talking about, the perfect place to find fossils. You have this high erosional, many layers of matrix coming down here, lots of erosion happening. So unfortunately, we haven't actually found any more material of Egomoshoshula yet. But what's really, really promising is that every time we go out, we find tons of stuff. So we're finding stuff just falling out of the hills here. This is just from we went a few weeks ago, and we found kind of a pig-like animal, a little neat. We also found a jaw and teeth of a little tiny deer, so a little miniature deer that used to live out there. So these are really exciting finds that mean we're on the right track. We're in the right place. All we have to do is go out and find some more until we find some more primates. But one really interesting new development that is really starting to get us excited about the future direction of this research are some new discoveries of Egomoshoshula. So here we've put up examples of all the material that has been found so far. And we've color-coded these with the stars to the location where they were found. So these blue stars are our beautiful Oregon fossils. This green one is the South Dakota. All of these down here were found in Southeast Asia. A really interesting thing that we noticed when we saw this specimen out of China is that it looks exactly like the one from here in Oregon. So if we had found this out in the Oregon fossil beds, we would have immediately put it in the group with the Oregon Egomoshoshula type. So what does this mean for us? What are we going to do with that? So when you put these out on the map to where they were all found, you start to get this big idea about how these primates might have dispersed themselves. So when we look at this Chinese fossil and the Oregon one, these are the two that look almost identical to each other. Even more similar to the ones that are found near each other. So what we're seeing is that the most likely route these animals took was originating here in Southeast Asia, moving all the way up through Siberia, across the Bering Strait, down into North America. So this is really exciting for us. So previously, this is not a route that had ever been considered one that primates might have taken. They were all moving to the west. They were all going through Europe, over Greenland, rafting to South America. So this opens up all kinds of new places to go explore for new fossil primates. So this is what we're going to do. This is what we're kind of looking forward to. We're going to continue looking here, but we're also really excited about the possibility of starting to find new sites up here that might be bearing other fossils that we could find. So this kind of brings you up to date on what we're doing and where our research is going. So send us some positive vibes. Cross your fingers for us that we'll continue finding things and maybe some new sites up here. And hopefully we've given you some idea of some new information that you didn't know before about primates, their history, and what fossils could tell us about their history, our history, and how we're all connected on this earth.
So we wanted to give a special thank you to the Academy of Arts and Sciences for having us here, for letting us talk to you about what we're passionate about. We have several other people to thank, including our collaborators and our funders. And most of all, we want to thank you for coming out and sharing some time with us.
Thank you. We brought a bunch of material of casts and examples of fossils. If you guys want to come up and take a look after this, we'd love to talk to you about them and answer any questions that you guys have.
So we'll hang out for a little bit. After everybody gets up, please help us stack the chairs, groups of 7, and just leave them there, we'll move them away. So let's thank our speakers once again. And,
Any questions for in front of the group? If not, you can come forward. Yeah.
So how do, in this particular situation or in general, how do fossil explorers manage to piece together a whole animal or visualize a whole animal simply from teeth?
Yeah, great.
It's a good question, yeah. So a little something called artistic license is involved in a lot of cases. And sometimes there's a lot of back and forth between paleo artists and paleontologists as to how things should look. And a lot of the stuff that you see out there is 90% imagination and 10% fact. So part of our work is to make it as anatomically realistic as possible. And so part of it is, being honest about what we have. And for this particular animal, you saw the reconstruction. It was sort of lemur-like, sort of tarsier-like. We have cheek teeth. That's what we have. So the artistic license comes in saying, okay, well, these cheek teeth look like the cheek teeth of a lemur. So all the other parts, we fill in with lemur parts. Anytime you hear that something is just a few parts anatomically, and they have a whole reconstruction, be suspicious of it, because there's a lot of artistic license that goes into that. When you have a full skeleton, there's a little less play, and it's going to be more realistic. So that's a very important part. When you're reading about any scientific discovery, what was the evidence?
I think it's also slightly important to talk about, with teeth, they're also really conserved. So their development and how they grow and the cusps that you see in teeth are very specific to species. So this can give you a really detailed idea and really hone in on what kind of species you're looking at, just based on little tiny cusps on the teeth. Because it's very difficult to change those things quickly over evolutionary time.
Yeah, it takes a lot of training to recognize what differences from one tooth to another are important and which ones are just random. And I mean, that's most of the training for mammalian paleontologists is, what bump's important, what bump's not, what tells you about diet, what tells you about parentage. Good question here.
You were mentioning that through teeth you would discover what they were eating,
Right.
but I imagine that what grows in a tropical forest today perhaps is not the same as what grew then, the fruits, the insects, etc.
It's true. So we rely on the paleobotanical record to inform those choices, right? So there's a pretty rich record of plants in the fossil record. And we have a pretty good idea of when the modern groups evolved. And Oregon is a great place for that question because in a different part of the John Day Formation, we actually have some of the best preserved 3D plant parts from the Eocene epoch. Things like seeds, nuts, leaves, stems, things like that. And plants have evolved much more slowly than animals. And so a lot of the things that we see today in the grocery store, we see first in the Eocene. Blueberries, cherries, things like that existed in the Eocene. They've changed over time. Humans have influenced this, right? And so fruits tend to be a lot fleshier. The parts that we're interested in are maximized, and the parts we're not interested in have been bred away. But yeah, we can get some educated guesses by pairing up with paleobotanists who understand the plant record. But that only tells us what they could have eaten, not what they did eat. Unless you get one of those really great preserved fossils where there's stomach contents and you can say, oh, that's, the seed of a walnut. It was probably eating a walnut. Yeah. Is there a question over here? Yeah.
What impact does the retreat of the ocean and land have on your ability to find anything on that migration?
I mean, that's a good question, because another component is you tend to find terrestrial mammals or continental mammals like primates on continental sediments. You don't tend to find them on oceanic sediments. And so if you're looking at a period of time where the ocean has transgressed up, so you have sea level rise, then the deposits at that geographic point are going to be ocean sediments. You'll find fossil fishes and things like that. And so you have to know what is the character of the sediments you're looking at. Is it continental? Is it oceanic? Is it from a river, from a lake? And yeah, that definitely affects where you should look when you're looking at that map. A lot of those Eocene rocks exposed in the geologic map are marine rocks, so we're unlikely to find a primate unless it washed down a river and into the sea.
But I think also the changes in that sea level rising is going to affect the human migration information more, because they probably were using boats to follow the shore. But with primates, they're following the trees, so it's much more likely that we will find fossils more inland and have more ability to find them. And I have, it's very hard to say, but with climate change, the positive is that a lot of these glaciers are going to disappear and reveal a lot of new fossil sites.
It's a silver lining, very thin silver lining.
Yeah, it opens up a bunch of northern Arctic territory.
Yeah.
So why don't we find many primates during the Eocene at the modern day tropics? Was it too warm for them there?
Another great question. So they are there. Those fossils are there, but they're covered in trees. So where we can look for dead animals constrains where we can find them, right? So there are tons of primate fossils undoubtedly in the Amazon rainforest, but they're covered in layers and layers of broken down tree trunks and other vegetative matter, and the living trees are there too. People are spending more time looking in the tropics now, but it's hard work because the fossil sites are like a little tiny patch beside a river. And you have to hope that that's where the fossils are going to be, because everything else is covered by trees. So another horrible thing to say is that droughts make us excited because we can, the vegetation dies and we can look for fossils.
We're not
Yeah.
Follow-up to that. So everybody knows what Olduvai Gorge is, first humans and all that, which is the desert part of Africa. So how do you know that the first humans weren't in the jungle part of Africa? You just haven't found them because they're under the trees.
Yeah.
Yeah.
They could be. Yeah.
Yeah, they could very well be. And in the African Rift Valley, people do find more early humans because there's more rock exposure. Africa's spreading apart, everything's falling down into the gap, and so there's a lot of exposure of rocks.
Easy place to find.
Easy place to find rocks, yeah.
All of paleontology is biased by where you can find fossils.
Yeah.
Any more questions? If not, let's thank our speakers once again.
Kind of animal as we have in Oregon.
Oh, yeah.
Yeah, so
Yeah, definitely.
just like that,
I know what's going on
but
out there. Yeah, it'd be cheap.
in our own state.
Funny, that was picture really great, yeah. This is private land.
Oh, yeah.
Yeah, good.
Second is an elementary teacher, and I'm just thinking of the fossil beds and stuff like that over the years, and trying to imagine how somebody like yourself knowing what you're looking at. It's like, how do you look at all those fossils and just don't see one age, but see all the multiple ages?
Oh, yeah.
Critters are.
It's hard. I mean, it's been a global effort to figure out, how the beds over here compare to the beds over here in time. In the big badlands in South Dakota, you got huge expanse of time. It's mostly Oligocene. But, that thing is from there.
Okay. What kind of age periods are we looking at?
So Oligocene, 26 to 18 million years, that kind of time period. The ones in Oregon are 29 million years. Yeah, so you probably walked over several fossils.